Yeah. Okay. Right. So now after this, what we have learned in the last class regarding the sensors used for the position. Actually, the sensors what we are discussing in the last class was the sensors which are used to measure the position, velocity, acceleration of the rotating member. Okay, that is nothing but your the encoders, which are also called as rotary encoders, or also called as the optical encoders. Right. Now, subsequently, now we just move on to some small different types of the sensors. We try to discuss now what are called as the temperature sensors. Right. Now, in this case of a temperature sensors, now basically these sensors are, as it is considered, comes under what are called as the thermal sensors, right? And these are mainly used to detect the changes in the thermal properties of the materials. Now that we need to understand what are all the possible ways by which the thermal properties are going to be changed. Okay, now thermal properties of the materials are the one what we are going to determine. Okay, now is to be determined. Right. Now when we say about the thermal properties of the material, now various properties are going to be, now when there is going to be incorporation, or when there is going to be the heating of the member is going to happen, possibility of what is called as the expansion, okay, or contraction of the members is going to occur. Okay, expansion or contraction of the solids, liquid and gases. Okay, right. Now you might have heard called as alpha. Any idea about alpha in terms of temperature? Any idea what is alpha? Alpha is coefficient of thermal expansion. Okay, that means what I am trying to say to you is, on the material, if you supply the temperature, okay, supply the, or if you heat the material, what is going to happen? The alpha of the material is going to change. That is the coefficient of thermal expansion, depending upon the material, depending upon the type of the material. Are you, can you able to listen? Is it clear?
Yes, sir.
Yeah. Okay. Now, depending upon the type of the material, thermal expansion of the material might change. That is, alpha is going to change. Now, what is that we are going to do now is, or we are going to determine is, we will be calculating what is called as the alpha. That is change in the expansion or contraction of the solid, liquid, or the gaseous material, whatever it is, by which I am going to measure what is the temperature. Okay. Right. Or what is going to happen? One is expansion or contraction of the material changes. Next is going to be thermal resistance may changes. Okay, the thermal due to the temperature, due to the temperature, thermal resistance may change. Due to the temperature, thermal resistance may change. Okay, right. And also the EMF of the material will changes. EMF will change. Okay, now what I am telling to you is, if it is going to be a temperature sensor, the thermal property of the materials are going to be changed, and that has to be determined. The various thermal properties are going to be, number one, the expansion or contraction of the material, okay, due to the fact of alpha, that is the coefficient of thermal expansion, or the resistance might change with the increase in temperature. Okay, some are going to be positive coefficient, positive resistance changes materials are going to be there. Some are going to be negatively coefficient resistance are going to be there. Then EMF will change. Okay, now these are the broad introduction to the temperature sensors. Okay, now in your understanding, what are the different types of temperature sensors that you can list now? What are the temperature sensors that you know? Just list, just tell me the name. That's it. Okay, we'll discuss later. Okay, names of the temperature sensor. Tell me.
Thermometer, sir. Thermometer.
Thermometer. Okay, the very basic starting point. Okay, from where you can able to determine the temperature. Very good. Okay, thermometer. Okay. Now the next question is thermometer. You know. Okay. Now what is the difficulty? You have to basically keep that center at a particular place so that you can able to measure the temperature. But in the mechanical element or in the mechatronics element, it is not always going to be possible for me to use the thermometer everywhere. Okay, right. Next level. Next level. Next level.
Thermocouple, sir.
Very good. Okay, next level is thermocouple. Fairly better. Very good. Okay, next. Any other than thermocouple? Temperature sensors, temperature measuring devices. Tell me quickly.
Sir, RTD, sir.
RTD. What is RTD?
Resistance temperature detector, sir.
Very good. Okay, RTD is resistance temperature detector. Okay, next. Next. Okay, you are told thermocouple. Sorry, what is that? The first one, thermometer. Okay, that's a common one. Then we have thermocouple. Then she told RTD, that is resistance temperature detector. Then we have what is called as thermistor. Okay, if you can able to recollect. Okay, there is something called as the thermistor. Okay, then there is something called as the thermodiode or thermotransistor. And then there's one more thing called a bimetallic strip. Okay, so some of the temperature sensors are going to be there. Okay, now we'll broadly discuss some various different types of temperature sensor. Let us start with what is called as the thermocouple. Okay, right. So let us forget about the thermometer. Okay, start with the thermocouple. Okay, now what are thermocouples? What are thermocouple? Basically, what is the principle of thermocouple? Thermocouple is basically used to measure the temperature. Now here what we have is when two different metals, okay, just observe, when two different metallic wires, okay, now this is called as metal A, okay, metal A, and we have metal B, okay, when these two are going to be fused together, okay, joined together and maintained at two different junctions, okay, that is junction 1 and junction 2, which are maintained at two different temperature, T1 and T2. Okay, there exists what is called as the electromotive force. Okay, this electromotive force, okay, is the measure of the difference in the temperature. This concept is what is called as the thermocouple basic concept. That means I'll repeat again. Thermocouple is mainly used to measure the temperature. If two different metals A and B are joined together, okay, if two metals are going to be joined together to form two junctions, that is J1 and J2. Generally, we will consider one junction as the cold junction at temperature T1 as maintained at 0, and other one is going to be called as the hot junction wherein the temperature is maintained at T2. Then in between which the electromotive force, that is nothing but what is called as a potential, EMF is nothing but voltage, EMF is nothing but voltage, or you can call it as potential difference, or you call it as electromotive force, or as voltage, it is one and the same. Now voltage is going to be generated. Okay, voltage is going to be generated, which is the basic principle of what is called as the thermocouple. And this effect is, by the way, if you know, this is called as Seebeck effect. Okay, this effect is called as the Seebeck effect. Okay, now this is the basic principle of the thermocouple. Okay, now the EMF E, okay, the EMF E is going to be dependent upon what is called as the temperature. Okay, now basically it is represented by the equation AT plus B into T square. Okay, now it's understanding that the value of temperature T1 will be what? What is T1? It is generally kept at what?
0.
Generally kept at 0 degrees Celsius. That is, we call this as what is called as the cold junction. Okay, we call this as cold junction. Okay, so kept at 0, and this T2 will call it as what is called as T. Now T is what now? T is the temperature. Okay, T is the temperature of the junction. Now E is nothing but EMF, that is what you are going to take, and A is going to be constant and B is also going to be constant. Okay, right. Then what are the materials that you can use? Any idea? Which are the thermocouple material? Any idea? Which are the thermocouple materials? Thermocouple materials. Yeah, which are the thermocouple materials? Forgot. Iron constant and
Copper, sir.
okay, right? Copper. Only one material will it make it as a thermocouple?
Constant and copper.
Copper,
Copper constant, sir.
copper constant and okay.
Nickel,
Then,
nickel
huh?
chromium.
Huh?
Nickel chromium.
Nickel chromium, chromal, alumel, nickel,
Constant and sir.
nickel constant and nickel chromium. Okay, these are all the combination of the material metals which are going to be there. Now, if you remember, you have done an experiment by called as JKT. Okay, that is calibration of thermocouple by using J-type thermocouple, K-type thermocouple, and T-type thermocouple. Okay, right. So these are nothing but those different types of thermocouple. Okay, now this is the possibility. Now, in order to make this to happen, okay, we have two different laws which are going to be there. Okay, there are two different laws of thermocouple. Okay, two different laws of thermocouple are going to be present. The number one is called as law of intermediate metal. Law of intermediate metal. Okay, right. Now, what law of intermediate metal states is, now what is the basic principle of thermocouple? If I have two different materials like this, okay, so this is metal A and this is metal B. Okay, then this is T1 and this is T2. What is going to happen? The EMF E is going to be generated. Okay, right. Now, the law of intermediate metal says, let's say this is metal A. Okay, now I will break this circuit. I will have one more metal called as C. Okay, just understand. Okay, now we have C, B is as it is there. Okay, now what is the effect of intermediate metal? Okay, this is T1 and T2. Okay, now here, okay, are you understanding what I'm telling? Now, this is the first case. Case number one is what? Case number one is the basic principle. That is, the electromotive force E is going to be developed when two metals A and B comes in contact with the two junction at temperatures T1 and T2, EMF E is going to be developed. Now, what is the effect of the incorporation of intermediate metal? I will have one more metal now. I was having AB, I was having iron and constant 10. I'll try to put copper in between. Okay, so this is iron and this is constant 10. I like to put copper. Okay, that is the third metal. The incorporation of third metal, okay, what is the effect of this third metal on the EMF? Okay, the law of intermediate metal says that, please understand carefully, law of intermediate metal says that the presence of or the addition of, okay, or the presence of other metal C in the basic circuit, okay, wherein you have metal A and metal B will not have any impact on E, will not have any impact on E, provided that the junction points at which you have joined the third metal are maintained at the same temperature potential, same temperature value. Now means, observe, you have added C somewhere in between the circuit. Are you understanding? You have added C somewhere in between the circuit. If you could able to maintain both the points at the same temperature, then EMF E will not going to be altered. Okay, that is the law of intermediate metal. Okay, I'll repeat again. Law of intermediate metal states that the addition of the third metal, into the thermocouple circuit will not have any impact on the EMF, provided that the third metal that you are going to add are going to be maintained at the same temperature. That's why I have written T and T here. Okay, if you change this to T3 and T4, then there will be change in the thermocouple. Means to say, you can still have a possibility of adding one more metal into the thermocouple. Okay, so that is the law of intermediate metal. Okay, then we have one more law, okay, called as, any idea? Any idea? Second one? Second one, any idea? Law of, okay, law of, okay, intermediate temperature. Law of intermediate temperature. Okay. So what is law of intermediate temperature states? Very simple. Okay. Now we have what? Two different metals, A and B. Okay. Maintain the temperature T1 and T2. The EMF developed is going to be E1. Okay. Right. Okay. Then one more is going to be there. Again, maintained at what? Maintained at same metal A and B, but maintained between the temperature T2 and T3. This gives you what is called as E2. Okay. Now, the law of intermediate temperature states that, okay, when a thermocouple is developed between junctions T1 and T2, E1 is the EMF developed, and maintained between T2 and T3, EMF developed is going to be E2. Similarly, if I am going to maintain the circuit with the same metal, but with what? With the temperature junctions at T1 and T3, EMF developed will be what is the EMF that might be developed? EMF developed will be equal to E1 plus E2. Please observe, understand carefully. Okay, right. So E1 is the EMF developed between T1 and T2. E2 is the EMF developed between T2 and T3. And if you maintain between T1, okay, of the first case and T3 of the second case as the extreme temperature of the junction temperature, the EMF developed will be equal to E1 plus E2. So this is something called as the law of intermediate temperature. Okay, right. Now this is about the thermocouple. But by using thermocouple, it is not possible for you to measure generally the smaller temperatures. Okay, right. Then the second method, okay, second one is called as what is called as bimetallic strips. Second one is called as bimetallic strips. Okay, right. Now what is this bimetallic strip is going to be? Just observe. We have something like this. Okay, I'm just drawing a bigger diagram for the better understanding. Okay, this is one metal. Whatever I am matching is one particular metal. Other one is as it is. Okay, right. Now we have two different metals which has clubbed together. Okay, though we have two strips of metal. Okay, please understand. Bimetallic strip. Simple. Bimetallic. Okay, there must be what? There must be two different metals. Bimetallic strips again is another case of measuring the temperature. So two different strips of metals are fused together. Okay, remember, are fused together at this point to form a rigid single structure. Okay, if you observe, this is not a two different structure. This is a single structure. Okay, right. Now, as we have two different metals, what should be the alpha of them? Will it be same or will it be different? Let's say one is steel, another is copper. Okay, is the alpha value of steel and alpha value of copper same?
No. No, sir.
No, definitely not. Definitely not. Definitely not. Correct. Now I will choose two different material, two different metals with different value of coefficient of expansion. Okay. Now this is the one. Okay. This is the metal with higher value of alpha. Okay. Right. This is the metal with lower value of alpha. Is it clear now? Clear? Okay, right. Now, the bimetallic strip basically is going to be used to convert. So is going to be used to convert temperature change. Convert temperature change into displacement. Now just observe what is going to happen. Now to this, I am going to supply the temperature. I am going to heat this metal. Means what? Is it I am heating one metal?
Both the metals, sir.
Okay. Now this is what? This is a single structure now. Okay. Now because you are fused together, both the metal pieces, and you are going to heat the single metal structure. Then what is the effect now? If you heat, what is going to happen? What is going to happen if you heat? one end is rigidly fixed. Okay, one end is rigidly fixed. You are heating the bimetallic strip material. Okay, what is going to happen upon heated? Which is going to expand more? Simple, no? We have two different metal with two different alpha. Alpha with high coefficient of expansion will start to expand more compared to what? Compared to metal with lower coefficient of expansion. Are you understanding?
Yes, sir.
Yes,
Okay.
sir.
Now, due to which, what is going to happen to this strip? Will the strip is going to be like this? What is going to happen to the strip?
It will expand, sir.
It will expand. Means what? Expand means what? Expand means what? Some location change is going to occur. Yes or no? Okay. Depending upon the temperature, when it's going to expand. Now you have to understand that when I am going to heat this bimetallic strip, the metal with higher coefficient of expansion will expand due to the expansion. Okay, it bends towards what? It bends towards the metal with
Lower coefficient of expansion.
it went towards the metal with lower coefficient of expansion, because the more expansion is going to be there for the top and less for the bottom. Therefore, what is going to happen now? Now, so I am drawing exaggerated diagram. Don't expect that this is how it is going to occur. Okay, I am just drawing an exaggerated diagram for you to understand. Okay, now earlier it was like this. Now it is going to become like this. Okay, are you understanding now what is that I am writing? Okay, now this is the one. Okay, now what has happened? If I take this as the reference, what is my D? Earlier, this was the basic point, that the top one. This is the top one. So what is this now? What is this actually? This is the amount of displacement. Now, if I take an inclination, so this is getting it or what? This is going to be your the zero reference point. This is the theta. That means what I am trying to say here is, now again I am telling, don't expect that this is the amount of expansion. No metal, okay, other than what is the plastic will never going to expand. It will just go away. Okay, right? So a steel and copper will expand. Okay, so steel and copper generally are going to be used. Steel with more coefficient of expansion and copper with less coefficient of expansion. Steel will expand towards the copper. Some amount of bend is going to be there. Okay. Now this amount of d or theta is due to what? This d, the displacement in terms of linear, theta in terms of angular, is due to what? Is due to what? What has made this d to come?
Heating, sir.
Heating, that's all. Okay. Now, the temperature that you are given, the heat that you are given is responsible for you to have the expansion of the metal. Okay. So, you will measure the value of D. So, larger value of D means what? Larger value of D means what? One of the metal has expanded largely. Okay. When the metal has expanded largely, it means it is susceptible to the temperature. Means it can take up the temperature and it will expand. So what if there is larger value of D? What is the value of T? And I am telling, I am not comparing the values. Literal, logically, if D is large, T should also be
Large, sir.
larger. Okay, so you are given more amount of energy, you are given more amount of heat energy, hence the displacement is going to be more. So, and also the value of theta is also going to be larger. Okay, now the concept of bimetallic strips is, it is mainly two strips of metals are going to be there, which are fused together and to form a single structure. The two metals that form the strip will essentially have different coefficient of expansion. So we have alpha 1 and alpha 2. Now alpha, let's assume alpha 1 is greater than alpha 2. If you heat the material, alpha 1, which is having a larger amount of thermal expansion, will bend towards the other metal which is having lesser amount of expansion, which is alpha 2. Okay. Now the amount of bending is nothing but theta. It is in the angular method, or the d, which is going to be linear. Okay, is proportional to what? Okay, theta or d is proportional to what? Is proportional to the temperature. Okay, right. Now we'll take that as theta. Theta will be equal to C into L into T. Okay, C into L into T, where what is C? C is what is called as the sensitivity of the bimetallic strip. Sensitivity of bimetallic strip. Sensitivity of bimetallic strip. And T, you can understand, T is the temperature. Okay, what is L might be? L is nothing but what? L is nothing but the length of the strip. Okay, length of the strip. So by using this, we can able to determine. Okay, so now what is this? C is constant. Okay, C is constant. L is also constant. Okay, right? Then the amount of theta is proportional to what is called as temperature. Okay, so by measuring the value of angular displacement, okay, you can able to measure what is called as the temperature which has come into effect. Okay, now this is something related to what is called as the bimetallic strips. Okay, is it clear? Can we go further?
Yes, sir.
Shall we go? Shall we go further? Yeah,
Yes, sir.
okay. So third one is what is called as the resistance, temperature detectors. Okay, RTD. Okay, right. So remember, very, very important is this is the most accurate. Okay, right? The resistance temperature detector, that is RTD, is the one which is most accurate. Okay, and in this case, what is going to happen? The largely it is going to be used. Okay, not sensitive to. Okay, very important. Not sensitive to external disturbances. Not sensitive to external disturbances. Okay, right. Now the concept of RTD is resistance temperature detector. Okay, right. When the temperature is going to be there on that metal, what changes? What changes? What property of the material is going to change? Now in the previous, what property of the material has changed? In the bimetallic strip, what property of the material has changed? When the temperature has given to the bimetallic strip, due to what property the deflection has occurred?
Heating, the length changed. Sir.
No. What is the property? Property. Which property of the material?
Thermal
Exactly.
expansion,
The
sir.
property of the material which has changed is thermal expansion. Thermal expansion of the material has changed. Because of thermal expansion of the material changes, you have got the value called as D. Now, in this case, that is the third one, in the resistance temperature detector, which property of the material is going to change? Which is the input? Input is what? Temperature. What is the output? The resistance. Okay. Now, in case of RTD, the resistance of the, very important, resistance of the metal, resistance of the metal increases. Okay. With temperature. Okay. With temperature in linear manner. Okay. In linear manner. Now, this is the property. Okay. So, this is the basic principle of your resistance temperature detector. Okay. Now, what is that relationship is going to be? Now, we'll just move on to the next page. Okay. Third one. Okay. Right. Once again, let me. Yeah. Okay. Okay. So what is the equation now? Okay. What is the equation? Okay. The equation is going to be what? RT will be equal to, okay, R naught into 1 plus alpha into T. Okay. So this is the linear equation. Okay. What is RT? Okay. RT is what? Resistance of the material. Okay. Resistance of the material at T degree Celsius. Okay. Right. Then R naught is resistance of the material at 0 degree Celsius. Okay. Alpha is temperature coefficient of resistance. Alpha is temperature coefficient of resistance. Okay, right. Now, this is the linear equation. Okay, so this is the linear equation which is going to be used. Okay, now, which are the RTD material which are generally used is important. Okay, now these RTDs are going to be a resistive elements. Okay, so these are called as the resistive element because they are going to change with respect to the resistance. Resistive element. Okay, now they are going to be present in the form of coils of wires. Coils of wires. Okay, the metals which are going to be generally used are going to be nickel. Okay, nickel, copper alloys, and platinum. Okay, remember this is the one which is largely used. Okay, this is the one which is largely used. Platinum is the one which is largely used, okay, compared to other cases. Okay, right. Now, if we understand the basic principle behind RTD, now as the name itself suggests, resistance temperature detector, RTD is used to measure temperature by correlating the resistance of the RTD element with the temperature. Which are the correlation factor here? In the previous, correlation factor was temperature and thermal expansion. In this case, the correlation factors are temperature and what is called as the resistance. Okay, so temperature is proportional to the resistance. Okay, now are we having positive coefficient of resistance here? Now remember, the RTDs are going to be are used with a range of 200 degrees Celsius to 600 degrees Celsius. Okay, right. Now the RTD is having, okay, now if I am going to take this as my temperature at degree Celsius, right? This is going to be the resistance. Okay, now this is what is the graph. Okay, this is the graph RTD material. The RTD material will show this type of graph. That means what? With the increase in temperature, there will be corresponding increase in the resistance which are going to occur. Okay, right. Now this is called as what is called as positive coefficient of resistance. Okay, this is called as positive coefficient of resistance. Okay, right. If you are going to take the slope of this, it is going to be what? The positive coefficient of resistance. That means what? With the increase in temperature, there will be increase in the resistance which are going to occur. Okay. So if you are going to consider what are going to be called as this is RT, that is resistance is nothing but RT because R naught is same. Then we have T. Okay. So this is going to be for nickel. Okay, generally, and this is for copper, and this is for platinum. Okay, right. Now platinum is going to show, okay, a gradual increase. Okay, in the linear range is going to be there. That's why this platinum is the one which we are going to be commonly used. Okay, right. That's about the concept of temperature RTD. Okay. Now, as I said, these RTD materials are going to be present in a shield. Okay, something like this. Now, as I told, it's going to be a wire. Okay, right. Now, this wire is going to be present in what is called as a shield. Okay, so this is nothing but your shield. Okay, and this is going to be the RTD material. Okay, that is nothing but what? The platinum material. Okay, so that's why this is not going to come across with the metal will not going to come across with the external disturbances. Therefore, so there is going to be an amount of protection. Okay, protection is going to be present for the RTD material. Hence, it is going to be generally used. Okay, it is stable. Okay, it is stable and it is accurate. Okay, accurate for the measurement of environment. Okay, so therefore, as it is going to be protected from the external environment, so this is going to be largely used. Okay, right. Then the next one we have is called as the thermistor. Okay, next one is called as the thermistors. Okay, now this thermistor, now in the previous case we have discussed this. What is there? The resistance of the material increases with the increase in temperature. Okay, that was the concept of RTD. But if you go to what is called a thermistor, okay, so thermistor is nothing but thermal resistor. Okay, thermistor is nothing but it is thermal resistor. Okay. Now the contrary to previous, this is the equation. Okay. So this is going to be a resistance. This is temperature. What can you say about this? Yeah. Now, can you say something on this graph? Can you say something on this graph? Compared to the previous? Previous was what? Positive coefficient of resistance. Now here what is happening? With the increase in temperature, the value of
Resistance.
the value of resistance decreases. Okay,
Decreases.
it is opposite to your RTD. Therefore, what is the property? So it is called as negative coefficient. Okay, negative coefficient of resistance. Okay, so just remember this, and contrary you can write like this. Okay, positive coefficient of resistance. This is negative coefficient of resistance. Okay, right? Now these are going to be the equation of this is RT will be equal to, okay, K into e to the power of B divided by T. Okay, now you can observe where the value of T is going to be, and that too it is exponentially reducing. Okay, the RT is nothing but what? Resistance at temperature T. Okay, you can understand this is resist. Okay, so this is resistance at temperature T. K is nothing but constant. K is the constant, and this beta is also going to be constant, and T is the temperature. Okay, now you can understand the temperature T and the resistance RT, it is inversely proportional. Okay, that means there is going to be a negative coefficient is going to be there. Okay, now these metals, okay, are going to be present in the form of, these thermistors are going to be present in the form of the discs. Okay, or they are going to be present in the form of the rod, or they are going to be present in the form of the bead. Okay, so disc is something but what? It is going to be something like this. Okay, right? So this is one and this is another. Okay, and then the rod type or the bead type is nothing but what? So this is connected like this. Okay, and something like this. Okay, now this is the way how the thermistors are going to be developed. A small construction which will be fixed onto the member. Okay, where you, for which you want to measure. So this you are going to fix it. Okay, right. So now they are very small basically. So these thermistors are going to be very small, which you can able to insert into any of the member, and it is generally used for what is called as a smaller temperature ranges. Okay, now generally these thermistors are going to be used for a larger temperature ranges. That is why we are going to consider this as another option. Okay, for the measurement of temperatures. Okay, right. Then to summarize, last one we have what is called as okay, the fourth one. Okay, can just finish it up, no issue. Okay, the fourth one is going to be what? Thermodiodes and thermotransistors. Okay, right. So what type of materials now? Okay, if it is thermodiode and thermotransistor, what is the type of materials which you are going to use here? Diodes and transistors. Okay, it is semi-conducting materials. Okay, you are going to use what are called as the semi-conducting materials. Okay, right. Now they are semi-conducting material. They are more, sorry, I not moved to the next slide. Sorry. Yeah. Okay. So the next one is thermodiodes and thermotransistors. Okay. Right. Then, so diode, we are going to use what are the diodes and transistor. Okay. Hence, they are the semiconducting material. Okay. What we are going to use is semiconducting materials. Okay. So they are semiconducting materials. Okay. Right. So they are sensitive to, they are more sensitive to temperature. They are more sensitive to temperature. Okay, right. Now what has happened? Now you have what is called as PN junction. Okay, just observe. Okay, Now, when you supply the temperature to it, okay, when you heat a diode, what is going to happen? The whole electron pair, the whole electron pair, which are going to be present over here, okay, over here, will knocked out. Okay, so they are going to be knocked out of the junction. Okay, means what is the meaning of this is, okay, right? What is the meaning of this is, now whenever the temperature is going to be there, so these valence electrons which are going to be present on the p-n junction will get energized. Okay, will get energized, and they will move out of the junction. And when they are moving, okay, they are going to carry the charges. Okay, they are going to carry the charges. Okay, now the amount of movement, okay, the amount of movement of charges, okay, are proportional to the amount of movement of charges are proportional to what is called as the temperature. Okay, right. Now this is similarly we have p-n junction, and similarly we have done what is called as p-np, and also we have done what is called as np-n. Okay, now as discussed in the light sensor, if you remember, the same concept we are discussing in the light sensor, but in the light sensor, with the application of the light energy, we are going to get the voltage. Okay, but here in case of the thermodiode and thermos transistor, now with the application of the temperature, the whole electron pair will be knocked out, which gives rise to the movement of the charges. When the charges are going to move, okay, okay, so there will be what? Now the movement of the charges will gives rise to, okay, the movement of the charges will gives rise to the voltage. Okay, and that is what I am going to determine, which is equal to the amount of temperature which is given. Okay, right. Now these are the different the temperature measuring devices which are going to be present. Okay, to sum up, the temperature sensors are, okay, temperature sensors is what we have started. Okay, so we have what is called, we have discussed what was called as the thermocouples. Okay, right. Then we have discussed what is called as bimetallic strip. Okay, then we have discussed what was called as the resistance temperature detector. Okay, then what are called as thermistors, and then what are called as thermodiodes, and thermo transistors. Okay, now these are the different methods used for the measurement of the temperature. Okay, right. Now I think 11:51, so we'll stop at this stage. Okay, then we'll try to understand the other type of the sensors in the next class. Okay, right. So we'll just stop at this stage. Okay, right. Now, thank you.
Thank you, sir.
Okay, all of you are there. How many? Yeah. Okay. 1 second. Let me just check. Yeah. Dhanush, Mithun, Monambal, Arsha, Srinidhi, Sukrit. Okay, right. Okay, fine. Okay, thank you.
Thank you, sir.
Thank you.
Rectification. You should keep in reminding me. It's separate. Okay. Okay. How was your today? Did you practice the figures? Okay. So take the textbook and go on, practice the sketches. Simply write, practice the sketches. Okay. Now Description is not more important. The proper sketch and the label. Sketch and the label. The figure itself is a self-explanatory. That is why. Got it now? Just to take a paper and pen and go on.